Most people assume the global economy is powered by oil, gold, or software. Those industries certainly shape the modern world. But beneath every digital transaction, every factory, every hospital, and every military system lies something far smaller and far more essential. A semiconductor chip, often no larger than a fingernail, has quietly become the invisible foundation of modern civilization. Without it, smartphones become useless, cars remain unfinished, data centers fall silent, and entire economies begin to slow. That reality became impossible to ignore when a global chip shortage forced some of the world's largest companies to halt production, costing industries hundreds of billions of dollars. Suddenly, a component most people had never seen was dictating the fortunes of trillion-dollar corporations and exposing vulnerabilities that had been hidden for decades. Governments responded by announcing massive investments, racing to secure domestic chip production, as if preparing for an entirely new kind of arms race. But why is manufacturing these tiny pieces of silicon so extraordinarily difficult? Why can't every country simply build its own factories? And how did a product almost invisible to consumers become one of the most strategically important assets on Earth? This isn't just a story about technology. It's a story about economics, global power, and the fragile systems holding the modern world together. To understand why chips became the world's most valuable building blocks, we first need to understand what they actually are. To most people, a semiconductor chip is just another piece of hardware hidden beneath a plastic cover. It's rarely seen, almost never discussed, and easily overlooked. Yet inside that tiny piece of silicon are billions of microscopic transistors, electronic switches that process information by turning on and off billions of times every second. Working together, they perform the calculations that allow modern technology to think, communicate, and respond. Silicon became the industry's material of choice because it possesses a unique balance of electrical properties. It can behave as both a conductor and an insulator depending on how it is engineered, making it remarkably effective for controlling the flow of electricity. That single characteristic transformed an abundant element found in ordinary sand into the foundation of the digital age. Today, semiconductor chips function as the brains of nearly every intelligent device. They unlock smartphones with facial recognition, coordinate navigation systems inside aircraft, manage fuel efficiency in modern vehicles, monitor life-saving medical equipment, power cloud data centers processing billions of online requests, and quietly regulate everything from washing machines to refrigerators. Even products that once relied almost entirely on mechanical engineering now depend on sophisticated computing power hidden beneath their surfaces. The remarkable part is not simply that chips are everywhere. It's that modern society has become so accustomed to their presence that most people never notice them until they disappear. Like electricity itself, they operate silently in the background, supporting industries worth trillions of dollars without attracting attention. But if these microscopic components are so deeply embedded in everyday life, why did the world only begin paying attention so recently? The answer emerged when one small disruption exposed just how fragile the entire system really was. For decades, semiconductor chips were treated as a reliable commodity. They arrived on schedule, disappeared into finished products, and rarely entered public conversation. That illusion of stability collapsed in 2020 when the COVID-19 pandemic disrupted a supply chain so interconnected that even minor interruptions quickly spread across the global economy. As factories temporarily shut down and transportation networks slowed, demand shifted in unexpected ways. Millions of people suddenly needed laptops for remote work, tablets for online education, gaming consoles for entertainment, and networking equipment to support a world living increasingly online. Chip manufacturers redirected capacity toward consumer electronics, assuming automotive demand would remain weak as lockdowns spread. Car manufacturers responded by canceling chip orders, expecting sales to fall sharply. Instead, vehicle demand recovered much faster than anticipated. When automakers attempted to reorder, they discovered that production lines were already committed months in advance to other customers. A shortage that initially seemed temporary quickly evolved into a global bottleneck. The consequences extended far beyond the technology sector. Assembly lines stood idle while nearly completed vehicles waited for a handful of missing components. Dealership lots emptied. Delivery times stretched for months, and prices climbed as limited supply collided with strong consumer demand. The same pressures affected medical devices, industrial equipment, household appliances, and countless other products that depended on specialized semiconductors. What surprised economists wasn't merely the disruption itself but its persistence. Unlike many shortages, this one couldn't be solved by asking factories to work a little harder or produce a little faster. Expanding supply required years rather than weeks, exposing just how inflexible the industry's production capacity had become. That raised an even bigger question. If demand was soaring, why couldn't manufacturers simply make more chips? Because semiconductor factories aren't ordinary factories. They're among the most complex machines humanity has ever built. The solution to a chip shortage might seem obvious: build more factories. But semiconductor manufacturing doesn't resemble a typical production line where capacity can be expanded with enough workers or additional machinery. A modern fabrication plant, commonly called a fab, is one of the most sophisticated industrial facilities ever created, pushing the limits of engineering, physics, and precision manufacturing. Inside these facilities, microscopic imperfections can destroy an entire chip. A single dust particle harmless to the human eye can be thousands of times larger than the tiny circuits being etched onto silicon wafers. To prevent contamination, production takes place inside ultra-clean environments where the air is filtered so thoroughly that it contains far fewer particles than an operating room. Engineers wear full-body protective suits not to shield themselves from the chips, but to shield the chips from them. The manufacturing process itself involves hundreds of highly controlled steps performed with astonishing accuracy. Machines repeatedly deposit, pattern, and remove layers of material measured in nanometers, dimensions so small that billions of transistors can fit onto a chip no larger than a postage stamp. Even the slightest variation in temperature, vibration, or alignment can reduce production yields and turn extraordinarily expensive wafers into worthless scrap. Building a facility capable of this level of precision demands enormous resources. Construction often takes several years, costs can exceed tens of billions of dollars, and success depends on thousands of specialized engineers, technicians, and suppliers working together. Once completed, the factory must operate at exceptionally high utilization simply to recover its massive fixed costs. These realities explain why new capacity cannot appear overnight. Manufacturing chips is not merely difficult. It is one of the most capital-intensive and technically demanding businesses on Earth. Which raises an obvious question. If fabs are this expensive, who actually has the ability to build them? Surprisingly, no single company or country controls the entire process. By the time a semiconductor chip reaches a finished product, it has already traveled through one of the most interconnected industrial networks ever created. Unlike industries where a single company can control design, production, and distribution, semiconductor manufacturing is divided across countries that each specialize in different parts of an extraordinarily complex process. Some companies focus almost entirely on designing chips, creating the intricate architectures that determine how processors, memory, and communication systems perform. Others specialize in manufacturing those designs at scales and precision levels that few organizations on Earth can achieve. Separate suppliers build the machines used to fabricate chips, while additional companies provide ultra-pure chemicals, specialty gases, silicon wafers, and other advanced materials required for production. After fabrication, many chips are shipped elsewhere for packaging, testing, and final integration before reaching electronics manufacturers. This specialization has created a supply chain built on global interdependence, rather than national self-sufficiency. The United States remains a leader in chip design and critical software. The Netherlands produces some of the world's most advanced lithography equipment. Japan supplies essential manufacturing materials and precision components. South Korea dominates large segments of the memory chip market. Taiwan has become the world's leading center for advanced semiconductor fabrication, producing many of the chips that power everything from smartphones to artificial intelligence systems. Each participant depends on the others. Remove one link, and the entire chain begins to weaken. A factory cannot operate without specialized equipment. Equipment cannot function without precision components. Designs cannot become physical chips without advanced fabrication. Even after production, testing and packaging remain essential before chips can enter the global marketplace. The remarkable result is an industry where no nation truly stands alone, despite every major economy relying upon it. But what happens when the world's most important manufacturing capability becomes concentrated in one place? That question leads directly to one island that has become the center of the global economy. Among all the countries participating in the semiconductor supply chain, one stands apart. Taiwan has become the world's most important manufacturing hub for advanced chips, producing the processors that power flagship smartphones, high-performance computers, cloud infrastructure, artificial intelligence systems, and countless other technologies. Many of the world's largest technology companies rely on factories located on this single island to transform their designs into physical products. This position was not created overnight. Decades of continuous investment, engineering expertise, operational discipline, and close relationships with global customers allowed Taiwan's manufacturers to master the most advanced production techniques. As chip designs became increasingly complex, only a handful of companies retained the ability to manufacture them at the smallest and most efficient process nodes. That technological lead attracted even more customers, creating a powerful cycle in which scale, experience, and innovation reinforced one another. The result is extraordinary concentration. Companies worth trillions of dollars often depend on the same manufacturing ecosystem for their most important products. If production slows, product launches are delayed. Data centers expand more slowly, and industries around the world begin to feel the effects. What appears to consumers as a delayed smartphone or a more expensive laptop reflects a much deeper dependence hidden beneath the surface. Yet this concentration also creates vulnerability. Natural disasters, geopolitical tensions, or disruptions to shipping could ripple across industries far beyond Taiwan itself. The obvious solution, moving production elsewhere, is far more difficult than it sounds. Building advanced fabrication capacity requires years of construction, immense financial investment, highly specialized talent, and a mature network of suppliers that cannot simply be recreated on demand. The world has therefore found itself in an unusual position, depending heavily on a single location, while simultaneously trying to reduce that dependence. That is precisely why governments have begun treating semiconductors not merely as commercial products, but as strategic national assets. Because semiconductors are no longer just products, they've become instruments of national power. For much of the 20th century, access to oil-shaped global alliances, economic influence, and military strategy. Today, semiconductor technology occupies a similarly strategic position. The difference is that modern economies do not simply consume chips. They depend on them to produce almost everything else. From advanced manufacturing and telecommunications to artificial intelligence and defense systems, semiconductors have become the foundation upon which national competitiveness increasingly rests. This shift has transformed chips from commercial products into matters of economic and national security. Governments now view reliable semiconductor access as essential for protecting critical infrastructure, maintaining technological leadership, and reducing exposure to external disruptions. Policies that once focused primarily on efficiency have expanded to include resilience, recognizing that the lowest-cost supply chain is not always the safest one. As a result, countries around the world have launched ambitious industrial strategies designed to strengthen domestic semiconductor capabilities. Tens of billions of dollars in subsidies, tax incentives, and public investment have been directed toward attracting fabrication plants, expanding research, and developing skilled workforces. At the same time, export controls and technology restrictions have become increasingly prominent, reflecting concerns that access to advanced chips can influence both economic growth and military capability. What makes this competition unusual is that success depends on far more than financial resources. Building a semiconductor ecosystem requires years of accumulated expertise, trusted supplier relationships, specialized equipment, and highly trained engineers. These advantages cannot be purchased overnight, regardless of how much governments are willing to spend. The global race is therefore about far more than increasing production. It is an effort to reshape supply chains, reduce strategic dependence, and secure a technological advantage that may define economic leadership for decades to come. But that raises one final question. Can any nation truly become self-sufficient in semiconductors? The reality is far more complicated than building more factories.